Do I make it bigger screen?
Yes. That's on that screen. Okay, so welcome everyone to first kids research talk of the year. And we have Tony Hunter with us today from the computer science department, and he's going to give a talk on computational persuasion. And we will record this talk if that's okay with everyone. And then we will share the recording with everyone in the department, and we'll also publish it on our website.
Great, good. Thank you very much for the invitation. Hello, everyone. So, my first aim is to get the slide order. Yeah, there we go. Yeah. Okay, so what I'll do is I'll talk about computational persuasion, and then I'm going to base the talk around three projects. The first one was a large, or at least for me, a large EPSRC project that's now finished. So I'll talk quite a bit about that. Then I'll talk about an extension that I did with a PhD student with EPSRC funding. And then finally, I'll talk briefly about an ongoing Cancer Research UK project. So the original project was with Emmanuel Haddo and Sylvia Polberg, two computer scientists who've now moved on. And we had the benefit of input from some experts in behaviour change, so Fiona Hamilton, Henry Potts, and Andrew Haywood. So the idea was that I'd heard about behaviour change, and this is quite a big thing in healthcare, in government, and so on. And the idea is to change people's behaviour in some small way that's good for them or for people around them. So eat more healthily, eat less biscuits that come from Greece, for example, take more exercise, and so on. But it can be other areas like wear seatbelts, recycle, vote, and so on. So my idea was to look at this from the point of view of persuasion and draw on argumentation. So persuasion is something we're all very familiar with. It's something we do constantly throughout the day. So here's a picture of a happy couple in a car showroom being persuaded to buy a car. So the persuader is collecting information, preferences, and so on, providing information, and so on. There's extra things like winning favour, flattery, and so on. But as the last bullet point shows, I think that arguments and counter-arguments are the key structures for persuasion, because they provide the claims and the counterclaims in persuasion. And so what I was interested in doing was drawing that into behaviour change. So I coined the notion of a computational persuasion system as being a system that can just enter into a dialogue with persuadee, a user of some sort, to persuade them to do something or not do something, or believe something or not believe something, via argumentation. So I'll make that clearer as we go along. And the primary aim is to persuade via providing useful information and overturning misconceptions. So this will become clearer as we're going along. So here's an example of the kind of dialogue that we were interested in. So this is a dialogue for persuading somebody a healthcare worker to take a vaccine. So this predates COVID, actually. And so the white boxes, it's a bit like a WhatsApp chat. So the white boxes are the chat bot or the persuasion system, and the green boxes are the dialogue bubbles for the user. So it starts with the chatbot saying that all hospital staff should be encouraged to take the flu vaccine. A supporting argument, hospital staff can infect patients, is provided. And then the user's provided an argument. The majority of hospital staff had no face-to-face contact. And then the chatbot comes back and says, but hospital staff are in the same building, breathing the same air, etc. And the user can say, well, there are disinfectant dispensers. And the chatbot comes back with infection can also spread through coughing and sneezing. So if you know anything about the literature on argumentation, you can see that implicit in there is the idea of the turn taking, and that the arguments made by the user have been attacked by arguments by the chatbot. And so the idea is that if every argument by the user has been attacked, then we could perhaps think that the probability that the user believes the initial argument is raised. And so this was the idea. Now, for these green arguments, the user arguments, in the original project, we didn't have natural language processing. So we had these menus. So this is a different topic, but supposing the chatbot said, to improve your health, you could join an exercise class. Then our chatbot would give a menu of arguments that the user could select. So they might say exercise classes are boring, and that's their counter argument. So that's in the original project, we just had these menus. So in the original project, we were primarily interested in what's called strategic argumentation. And so the idea is that the chatbot enters into a dialogue, and the chatbot tries to make strategic choices of move to make to increase the probability that the dialogue is persuasive. So the three interrelated topics that we focused on: how we model the domain, so the subject of argumentation; how we model the user, so we could optimize the choice of moves; and the strategic dialogues, how this was done. So I'll say a little bit about each of these boxes, and then I'll talk in detail about some applications that we did. So domain models. So our starting point was what's called an argument graph. So if you know anything about the literature on computational models of argument, this is probably the first thing you heard about. So this idea comes from Fan Min Dung some time ago, and the idea is you can represent a set of arguments and counter-arguments by a directed graph. So each argument is abstract, it's just an atomic entity, and it's represented by a node in the graph. So we have here 9 arguments. And then each arc denotes a relationship between arguments, where the one is a counter-argument to the other. So the argument that has an arrow coming into it is being attacked by the source argument. So for example, A1 is attacked by all the B arguments. So each of the B arguments is a counter-argument to the A1 arguments. And similarly, C1 is a counter-argument to B1, C2 is a counter-argument to B2, and so on. So we use this as our starting point. And so the idea was that we'd have both the arguments that the chatbot's using and the arguments that the user might use in this graph. So there's kind of omniscience assumption. So it might be that A1 is the starting argument the chatbot gives. And supposing B3 is what the user gives, this one highlighted in yellow, then what we want to do is attack B3. So we just take that from the argument graph. So this was the essential idea, very obvious application of argument graphs. So then we wanted to, and I'll say more about this a bit later, we wanted to build some demo systems. And so we wanted to build these argument graphs. And if you look at the literature, there's actually quite a lot of literature on reasons for changing behavior. So reasons for taking exercise, reasons for eating healthily, reasons for taking a vaccine. But interestingly, there's much less on reasons for not changing behavior. So here, if we want this graph, we can get A1 and C1 to C4 quite easily, but there's much less literature on B1 to B4. So and we need this to be able to have meaningful dialogues and think strategically. So what we had to do was develop some crowdsourcing techniques. And so I'll say more about that a bit later on. But we were able to do this and build some quite big graphs. So, I mean, the reasons that people give, there are ontologies within health psychology literature, and that there are various kinds of argument, but they don't document for a given problem. So here are just some that people talk about. So the first one is when the agent fails to take responsibility for a problem. So I am overweight because drinks companies make soft drinks too calorific. It's not my fault, in fact, it's the drinks companies that are at fault. Or risks. People say drinking a large quantity of alcohol at the weekend is okay because I do not drink in the week. This is fallacious. So people have biased views of their own risks, and so on. And so we want these kinds of arguments. So that's the domain model. The next is the user model. And so in the user model, we focused in the project on 2 dimensions. The first was on belief in arguments, so the belief that the argument is acceptable. And the second is concerns. So I'll just say something about belief in the example below. So here's a simple argument graph. So this could be a scenario where I listen to some friends who are talking about a picnic. So one might say argument A, John suffers from hay fever, so a picnic in the hayfield will be unpleasant for him. So this might reflect John's problem. Another friend might come and say, well, John has taken a homeopathic medicine for hay fever and therefore he won't suffer from hay fever. Now, if you just stop there, I'm just listening to that, and there's no more arguments in play, it would be quite natural to say, well, B attacks A, so I believe B, and I don't believe A. And this reflects what people do with computational models of argument. They do this in much more complicated graphs. But the problem here is I don't believe B. I don't believe homeopathic medicine works at all. So I can't join in the conversation, perhaps, because I'm being diplomatic, or maybe I'm just listening to it and I don't have an opportunity to speak. I don't believe B. So I want to run counter to what is normally done in the argumentation literature. I want to be able to disbelieve arguments. So here I might completely disbelieve B and believe A highly. So this is what I mean by a probability assignment to arguments. Concerns I'll talk about a little bit more later, but essentially this is, when you look at arguments, often they raise concerns or they address concerns. And concerns, you can often see concerns in arguments, but different people have different concerns that are important to them. So if we're talking about cycling, I might be, if I'm cycling in London, safety is the most important thing to me. And perhaps the local economy is the least important to me. And so I might be able to rank these concerns, and we'll talk about this a little bit later. So then we come to dialogues. There's been a lot in the argumentation literature on dialogues, how you can have different kinds of moves, how the agents, persuader and persuadee, can take turns, and you can have different kinds of dialogues, but one is persuasion dialogue. And so obviously the aim is for the persuader to persuade the persuadee to believe something like, you eat too much fast food and you should try to eat 5 fruit and veg a day or whatever. And there's plenty of work on protocols that specify what are allowed moves each step in the dialogue. Now, what we were focusing on was strategies. And so this is an area, there has now been some work on this, but there's a lot more to be done. And it was an interesting topic to work on when we started the project. And so the thinking is that if I'm a chatbot or I'm a persuader and I'm trying to persuade you about something, I may have a choice of arguments to present to you. And if I know something about you, I've got some model of you, I can make a choice, an intelligent choice. Instead of just applying a random strategy, just where I randomly pick a move, I actually think, what is likely or more likely to persuade you, and make an informed choice. And so we looked at a local strategy where you just look at the next step, out of the available moves, what's the best move to make. And we also looked at a global strategy where you actually think about it as a game theoretic problem and choose a policy for the whole dialogue. So you actually think about it in depth. So I'll say more about both of these. So the local strategy, this gives a little bit more depth to the idea of concerns. Supposing you've got the first bullet point has an argument. The user is given the argument. So this is for a situation where we're trying to persuade the user to cycle to work. And so the user might say, building cycle lanes is too expensive for the city. And supposing you as a chatbot have just got 2 arguments. One is evidence shows infrastructure for cyclists favours the local economy, generating more taxes for the city to use. And the other is cycling is cheaper for citizens than driving or public transportation. And so we might label those arguments. And the first one is about the city economy, so that's the concern. And the second one is the personal economy, so arguments 1 and 2. And supposing in our user model, we've got this ranking. So the person thinks personal economy is by far the most important thing, and city economy is the least important thing. Then it would be natural to pick argument 2 as opposed to argument 1 as the argument to present in the dialogue. So this is something we explored empirically. Now, the global strategy, I don't want to get into this in too much detail, but the idea here was we were looking both at concerns, but also probabilities. And so I mentioned this idea that you could have a probability function that you could use to assign a probability value to particularly a key argument, but maybe all the arguments in the dialogue. And so that could be at the start, you have P0, so you can see in the top box there, P0, and this would be your user model. And then as each move is made, so move M1 with P0 leads to an update of that probability function to P1, and then M2 leads to P2, all the way to at the end, by the time Pn is, move n is made, you end up with probability function Pn. And so it's that last one we're predominantly interested in if we're thinking about optimizing the dialogues. So I won't go into any of the details of how we do that, but just suggest that we do that. So for a global strategy, essentially what you do is, at least in theory, you simulate the construction of all the possible dialogues. So you can think of it as a tree. And we started just using the same kind of ideas that people use for chess and other games. So each branch is one game, so to speak. So in our scenario, each branch denotes a dialogue. And what you do is you construct the game tree, or the dialogue tree with all the leaves, and then you have a utility function that assigns a utility value to the leaves. And then you use a method like minimax, which is quite well known, and pass the values back, and you use this to decide on the optimal policy. So we did some work with simulated dialogues that we published, and I'll say a little bit more about how we used it for a practical system. More recently, and this will give you a little bit of an idea of this idea of games, we've been looking at games in extensive form. So here, this is a generalization of the idea, but should illustrate how you could use minimax as well. The idea is we've got two utility functions, one for the persuader and one for the persuadee. So if you look at the leaves, these are the values that we've assigned. So the first number is what the persuader would get out to get into that point of the dialogue, and the second number is what the persuadee would get. So each branch denotes a dialogue. So you can see they're very short dialogues. So the root is the point where the persuader or the chatbot's making the decision. Should it say argument A1, you can join the office daily walk to get fit, or argument A2, you should join the office daily run to get fit. So there's a choice there. What's the best to do? Then the next level down, the user is making a move. So they're only allowed to make one move, and then the dialogue finishes. So I won't go through all of them, but you can see, for example, on the leftmost branch, so the dialogue is, you can join the office daily walk to get fit, and the user might say, I will join because walking with my colleagues will be fun. And so we end up with all of these dialogues, and somehow we give a utility score. And so you can see from the point of view of the persuader, the branch there that ends on leaf N7 would be the best. But it's not necessarily the case that you would get that. If the persuader takes that branch, says A2, it may well be the case that persuadee picks A7. So the way the utilities work is when it's a persuadee move, so we go up from the leaves upwards, you pick the maximum number out of the persuadee numbers. So we've got -8, -1, and 0. So 0 is the maximum. So that's why we pass up the utility for 0. And so it means that if you ended up at N3, the persuadee would go down to N8. And then on the right, at node N2, the maximum for the persuadee is 6. So that's the value 3/6 past that. Now then at the root, it's the persuader. So they look at the first number. So they either get 0 or they get 3. So they pick 3. So that means the optimal policy for the persuader is to say you should do the office daily walk as opposed to office daily run. in the expectation or the hope that the persuadee would then say A4. So that's essentially the idea. Okay, so we did, in the main project, we did some studies with users. We did one on cycling and we did one on student fees. So the cycling one, we built a graph with 51 arguments on the topic of cycling in the city, and we had 8 concerns. I won't read them out, you can see them there. We also did some pre-studies with participants. And so we found that participants tended to agree on the assignment of concerns to arguments. So we give them all of the 51 arguments, and we split them up into groups of people, and they would systematically have a good overlap in what they would assign. Secondly, participants would give meaningful preferences over types of concerns. So we gave them the 8 concerns, and whilst they weren't able to rank them completely linearly, sometimes we did get some cycles that tended to be lower down. So we got useful information out of that. And interestingly, thirdly, if we gave them an argument and gave them a list of counter-arguments, users tended to pick the counter-argument that corresponded to their concerns. So they were actually playing by their concerns. And so you look at the data, we had a strategic system that used this local strategy of using concerns and a baseline system that just randomly picked. And you see the strategic system, 6% went from negative to positive. So we asked them before and after about whether to cycle by city. And none went from positive to negative, whereas the baseline was almost equal number went from negative to positive and positive to negative. So it was statistically significant difference. So this gave us some encouragement. The second system we developed was an argument, was on persuading people about university fees. So if they believed that the £9,000 fees were a good thing, we tried to persuade them it was a bad thing. If they thought it was a bad thing, we tried to persuade them it was a good thing. So it was not a behaviour change application, but we found that in practice, if you stuck to behaviour change, it's quite problematic. Because if somebody said, if we were trying to persuade them that dieting is good if you're overweight, you can't persuade them. If they said, yeah, I agree, dieting is good, you can't then persuade them that it's bad. You know, it's an ethical dimension. Whereas this is not so unethical. Anyway, we constructed an argument graph. There were 150 arguments and 10 concerns. We crowdsourced assignment of concerns and beliefs to arguments using over 400 participants. This was all done on a crowdsourcing website. And then we compared our chatbot with a baseline system with 260 participants. The difference in performance was less marked than the previous one, but it was statistically significant, the difference. And I think if we'd done some more work, tweaked it, we would have got better results. So that's the first part of the, I'll skip over that. And what I want to now talk about is some more studies we did. And this was with a PhD student who finished last December. And she saw what we were doing, and she wanted to bring in a natural language interface because we felt that this menu was a little bit of a, it was okay, but we thought a natural language interface would be interesting. So she did a few things. She worked on crowdsourcing. So one of the things we did was she looked at this university fees domain, and for us to develop an argument graph with 150 arguments on university fees, it took a couple of people over a month working on it full time. It's hard work. And the bigger the graph is, the longer it takes. It's non-linear in terms of the number of arguments. If you want an argument graph for 10 arguments, it's quite quick. 100 is quite long. 1,000, I don't know. Whereas what she did was crowdsourced it and got a very nice argument graph with over 1,200 arguments in it. And she used that for a chat box. So this is the pipeline. So the user types in an argument. So we ran this chatbot. We did the first one we ran on Facebook, actually, so you can just embed it on Facebook. So the user just types in an argument. And then what our system does, or what her system did, was it just used word embedding. So it used the words in the sentence, taking the word embeddings from glove, and looked at cosine similarity. And looked at the graph to try to find similar arguments. And it would find, if it found a similar argument, then that would be the reply. We found multiple similar arguments. So we're on the left branch now. It would look for the concerns, essentially looking at keywords and with a classifier, worked out what the concerns were of the user, of the user argument, and compared it with the concerns in each of the possible counter arguments and made the best pick. So the one that maximised the overlapping concerns.
Did it ever have problems with the valency of the argument? Did it ever find counter arguments that were supporting the person's original just because of the way it was matched?
Off the top of my head, I don't remember that being a problem. But now you say it, I would have thought it would have been. I'm sure it would have happened some of the time. So that would be how we would pick the system argument. But quite often it wouldn't find a match. And so we have some default arguments. We had a repository of half a dozen default arguments. And so we ran this on Facebook with 50 participants, one for a baseline system where we didn't do this concerns bit, and the other with the strategic one that did. And we asked them before and afterwards what they felt about their stance. So the top top box gives some results. So on average, it took 24 turns, so 12 for the chatbot and 12 for the user, which I thought was quite long. And just over half were default arguments, but nonetheless, if you look at the dialogues, they don't look bad. Now, the results, the middle box is the important thing. So if you look at the change in stance, the row, the number of participants, the baseline system, 41 didn't change their mind. 5 actually went to the negative, so they changed negatively, and 4 went positively. Whereas you look at the strategic one, only 26 didn't change their mind, and 23 changed their mind positively. So this was, I thought, quite impressive. If you look at the quality, the things are much more mixed. So we asked them whether they felt they were understood, whether the arguments were relevant, and whether points were addressed. And I think it's only on whether the user thought the arguments were relevant did we see a difference between the strategic system and the baseline system.
Can I ask you something? What are the CS points?
So what we asked them before was whether we used the Likert scale, whether they strongly agreed, neutral, strongly disagreed, or disagreed. I gave that in the wrong.
Yeah.
So you've got a 5-point scale. So these were the points.
So you measure.
Look at it, because we added up the number of points. We've got 23 people who changed either from negative to neutral or negative to positive, or from neutral to positive. But it was not that they would move, say, from strongly negative to strongly positive. They would maybe move from weakly negative to weakly positive, or neutral to weakly positive. So that's what that tells you. Okay, so then she did another chatbot on COVID, and so she had 100 participants to give her arguments against taking the vaccine. So it's not this arguments for taking the vaccine, just arguments against the vaccine. And she collected over 300 arguments and then just did some simple clustering into 15 groups. So the argument graph was much simpler. And then the counter arguments were taken from places like the NHS, and they were checked over by healthcare professionals. The second bullet point shows we ran it on a dedicated chat interface because it was simpler. Actually, we decided to just move to our own system rather than using Facebook. She ran it with 240 users. We didn't have a baseline system. The dialogues were shorter because there were fewer arguments. People had less to argue about. With university fees, people have quite a lot to say on it, and there's some kind of sophistication to what people can say. With the COVID case, the kind of arguments people were coming up with were the things that we all heard about. And there weren't that many, really. So the dialogues were shorter, they were half the length of what we had before. And so on average, the chatbot gave 6 arguments. And again, it was similar. Half were default and half were from the graph. I won't go through all the results. If you look at the middle box, this was the results in change in stance. So 9 people went from negative to neutral. It was the same 5-point Likert scale, but so negative to neutral. 7.5 went from neutral to positive, and 3.5 went from negative to positive. So 20% was shifting their views, which we thought was actually quite impressive.
And they were negative or neutral to start?
No, if you look at the top box, so that's the 5-point Likert scale. And before, 30% were very unlikely, 42% were somewhat unlikely. So nobody was positive before.
Yeah.
That might have been some filtering, actually.
I mean, it would make sense if you're persuading positively to only choose people who would.
I think that was what we did. I forget. And then afterwards, you can see what happened. There was this shift to quite a lot of people were moving to neutral, which is something. But you can see 10%, over 10%, came over to somewhat likely or very likely. So 10% actually really became quite positive about it. And you look at the results about whether they felt understood, relevant, and concerns addressed. They're not too bad. I mean, we're not comparing it there with anything, but we did compare it here. So we compared it with, this was a separate group of participants. We did a comparison of a chatbot with a web page. And so this is what we had at the start. So 60% were very unlikely with the chatbot and 52% very unlikely at the start. And it just so happened, so you can see that's what at the start of the study. And then the second table gives what we had at the end. So we had 11% were moving positively in the positive direction using the chatbot, whereas only 5% who had the same information but given in a web page.
So how does 12 plus 5 plus 2 equal 11? No, it's not 19.
Off the top of my head, I don't know. That could well be the case. I'm just worried there's something else going on there and I'm not explaining it. Let's say it's 19. Okay, so I'm coming towards the conclusion. So we've got our current project. So this is funded by Cancer Research UK for 12 months. And as the first bullet point says, what we're trying to do is develop and evaluate a chatbot to persuade people to participate in bowel cancer screening. So here the idea is there's a simple test that you can do at home, and it's very good for screening people. And a lot of people don't take advantage of it. And this one, we're collaborating with a group of people from UCL Department of Behaviour Science and Health. So they're real experts in bowel cancer screening, and they do all sorts of psychological studies. So we're crowdsourcing the barriers to the counter arguments, reasons why people don't want to participate in screening. So we've crowdsourced many arguments. We're also using what they call co-development workshops, where we get volunteers to come along, and I don't go to them because I don't want to interfere with it. They tell them about this and they give examples of dialogues and so on, and get feedback on the protocol and a lot on the phraseology. So when I write these things, I say things like, you should do bowel cancer screening. People throw their hands up in the air saying, you cannot tell people what to do. You should use nice language. Like, have you thought about participating in bowel cancer screening? All this is very important. So we've developed a chatbot. It has no model of the user, has no strategy, because it's the preliminary study, and I just want to get something working. So it's updating what Lisa did, and it uses a large language model. So on the third bullet point, it says it uses the Robert large language model. But if you know anything about large language models, it's Roberta. But nobody, I guess you're not using them, so you didn't balk at that. The picture at the top shows you, it's similar to what Lisa did, but it's different as well. So the user puts in the input, each turn they give their user input. And what we've used is this large language model. We've used it as a text classifier. And so we've got a number of classes of argument that the user might give. So it might be they haven't got enough time, or they find the whole thought to bowel cancer, the test which involves taking a sample of your feces, disgusting, or they can't be bothered, or they feel they're healthy. There's a whole range of reasons why people don't want to do it, or don't think they need to do it. And so we know about all of these because we've crowdsourced all of this information. And our large language model, it just classifies the user input as to the type. That's what we call intent. So it's just a text classification.
In terms of whether it attacks or supports?
No, it's not even that. We just assume they're attacking. And so all we were trying to get is what do they mean by their argument, their input? So is it them running out of time? Do they think it's disgusting? So we've got all these different intents, these different classes.
Is that similar to the concerns that we were talking about?
No, it's not.
Okay.
But you could imagine it's related, but it's really just what is their argument. Okay. I mean, there's clearly an overlap in the notion of a concern and this notion of intent, but you're not coupling them. We're not doing anything strategic. So you just give me your argument. I try and guess what you mean roughly. I just have a number of buckets and I try to guess the right bucket. And then once I know what the intent is, which bucket you're in, I go to my database of responses that are all written by healthcare professionals and checked over and give that answer. So it's a little bit like what Lisa did with the COVID system. So that gives the output. So it's just a simple cycle. And there's a little bit of protocol that I don't need to give you how it starts and how it ends. And the evaluation we're going to do is, instead of using crowdsourced participants who we've been paying, like Amazon, Mechanical Turk and Prolific News, we're doing evaluation with what's called walkthrough interviewing. So again, I won't be involved in that. It's going to be these other people who are perhaps a little bit more neutral. And they'll talk to lots of people and go through it. And as the person is going through it, they talk about what they think, like, this sounds rude, or this is not relevant, what I'm worried about, or this would change my mind, I'd never use this, or this is fantastic, or whatever. We just collect all of this in a qualitative way. So that's that. I'll skip that and just go straight to the conclusions. So the conclusions are computational persuasions based on computational models of arguments, which is this subfield of AI. And I claim that it's a promising approach to developing technology for behaviour change. We're continuing to work on the framework, so we're looking more at strategic dialogues. We're looking at, currently we're just using abstract argumentation, but I'm very interested in more structuring arguments. And so currently what I'm looking at is how you can bring logic into this. And that then raises problems of dealing with enthymemes, where you've got incomplete premises and conclusions. And then we're looking at how you fill that in with contextual knowledge and common sense knowledge. And I would like to do more evaluations with participants if we can get funding. Otherwise, I'll just carry on doing theory. So, there we go.
Okay, thank you.
Stop the recording.